this third speaker for the day will be Hassan Ghasemzadeh. He is an associate professor of computer science here at the School of Electrical Engineering and Computer Science, and he will be talking about machine learning for mobile health applications.
Today I'm going to talk briefly about several projects at the intersection of machine learning and mobile health that we have been doing in my research lab in the past 7 years. So I'm going to, in the interest of time, I'm going to talk only briefly about each project to just stimulate discussion and promote collaboration rather than digging into details of projects. So my research is motivated by a number of facts, including the increasing incidence of chronic conditions. We know that according to CDC, 60% of adults have at least one chronic condition. 40% two or more. In elderly, we know that 80% of seniors have at least one chronic condition, and most of them have more. So as a result of this, the burden on chronic condition is huge. In fact, we're spending $3.5 trillion on healthcare each year. The majority of that is due to actually chronic conditions. And in the US, we're spending twice as much on healthcare as any other advanced country. And this is also despite the fact that these chronic conditions actually can be prevented, or the onset of those can be delayed, right? So with these motivations, the idea is how we can go from an acute care setting where we're spending a lot of money on healthcare, and it's also only reactive care, to an in-home care monitoring setting where we can provide, care anywhere and any place, and this would be more an proactive care, preventive care solution. So how do we do that? Mobile health is one solution to this problem. So here we see a number of off-the-shelf sensors. This is a wristband for stress monitoring we've used. There's blood pressure, weight scale, Fitbit, and other devices. So there are devices that we have developed: the smart bottle, smart shoes, smart sock, and other devices, wearable and mobile devices that can be integrated into environment, can be worn on the body. And once we have these sensors available, we can extract various biomarkers of health, including activity, gait, diet, stress, and so on. Once the biomarkers are detected, we'll be able to provide interventions in various forms, from providing simple prompts to increase actually medication adherence, to providing notifications about an adverse event occurring, to providing recommendations in terms of the proper course of treatment. And as we do all of this, we have to address specific challenges of designing these systems. For example, reliability of these systems, energy efficiency, security, and privacy of these. All of that needs to be addressed for successful development and deployment of these technologies. Now, I want to look at a few technologies, few application areas that we have developed in the past with the focus on gait, fluid intake, edema, medication, stress, and diet. So the first one is gait. We have designed this smart shoe system that you see here, device, which includes various types of sensors such as accelerometer, Bluetooth, here, pressure sensor, microcontroller, and also it includes basically pressure sensors that are integrated underneath the insole. And this technology is actually complemented by machine learning for the purpose of mobility assessment. With this technology, we're able to detect gait cycle. We are able to extract various gait parameters. We can estimate fall risk. And we have deployed this in various settings, including patients with glaucoma and children with Rett syndrome. In one instance, for example, we have been able to extract biomarkers which are specific to a particular disease, for example, glaucoma, that suggests that there is a potential for designing biomarkers that can actually allow us to predict development of these diseases. Another example is fluid intake. So here we have designed this, what we call smart lid, a number of sensors that are integrated from inside into the lid. In this example, it's an ultrasound sensor which measures distance from surface to from the lid to the surface of the liquid, and also basically RGB color sensor which allows us to detect the type of fluid. This is also complemented by machine learning algorithm which detects the type of fluid, which can estimate the fluid volume, how much you're drinking from this bottle, and also calorie intake associated with different fluids. So we have examined this with water, coffee, you name it, all kinds of juices and all that. So edema is another marker that's important. It's a symptom in a number of diseases, such as heart failure. So current approaches for edema monitoring include clinical visits, self-report, or using a weight scale as indication of fluid retention. So we have designed the smart sock platform that you see here. It integrates stretch sensors in multiple locations. It detects the body posture and is able to actually tell us the lower limb edema and keep track of that over time. So another example in medication adherence, we know that medication non-adherence costs us $289 billion each year, and medication non-adherence is about 50%. So therefore, it's important to design technologies that improve medication adherence. So in here, we have designed machine learning-based approaches which use sensor data, specifically basically sensors embedded in smartphone and mobile devices to provide adaptive or context-aware medication prompting to basically improve medication adherence. Stress is another marker which is important. Stress is the body reaction to physical or psychological threats. We know that. And stress triggers a number of physiological responses, including, for example, skin conductance, heart rate variability, and skin temperature. So we have used existing wearable devices such as wristband, which is Empatica E4, in clinical studies to collect data and detect machine learning algorithms for automatic stress detection. This is collaborating with our colleague in human development and College of Medicine. And the study includes basically collecting data about skin conductance, skin temperature, and heart rate in patients recovering from alcohol dependence. Another example is diet. Diet, we know, is a very important biomarker. Existing techniques to measure biomarker include, for example, wearable sensor. You see here is a necklace which allows us to detect eating moments. Or there are mobile apps where you can actually take an image of what you're eating, and it gives you an estimate of calorie intake. There is mobile, again, apps where you can enter exact amount of food that you're taking. It gives you an estimate of calorie intake. So what we have done is design a new kind of modality for diet monitoring based on unstructured data, including speech and text. Basically, you can speak to your phone or type in, and it actually uses natural language processing, speech recognition to basically compute the calorie intake. Of course, there is a backend database attached to this, which uses input data and references against USDA nutrition database. So the system can compute calorie intake, can suggest diet recommendations also, so it can be used for diet planning or recommendation. So with these few examples of technologies, I want to also touch base on a few challenges related to reliability. Of course, there are reliability, energy efficiency, privacy, and security concerns about these systems, how we can design mobile health systems that provide actually accurate machine learning outcomes. They're power efficient enough that can last for long enough for days or months before recharging the battery, and so on and so forth. Specifically, I'm going to talk about two projects that we have in this regard, which address cross-domain performance decline and also catastrophic forgetting for these systems and other machine learning AI systems. To focus on these, I want to talk a little bit about difference between humans and machines, right? So humans do not learn everything from scratch. If you learn how to bike, so you have developed certain skills that you can leverage once you buy a motorcycle. So you can easily ride a motorcycle or learn how to ride without basically learning everything from scratch. But machines are not like that. They fail when basically they fail to accurately classify events when there is a distribution shift in the data. So here you see a simple, classifier, linear classifier, which can distinguish between these two classes, red and blue. But due to a distribution shift, when it's adopted by a new user, the system is adopted by a new user, or various aspects of the system changes, the model remains the same, but the distribution of data changes. Therefore, the model starts making wrong, actually, predictions. And we have looked at this from different angles. Here you see smartphone data, two smartphones, LG and Galaxy. So they're being used for activity monitoring here, right? So because of various changes or differences between these two smartphones, if you design a machine learning algorithms using this, we call it old, let's say, smartphone, and try to apply it on the new smartphone, you get 22% reduction in the accuracy of the system. Another example is cross-user performance decline. If you learn a model using a bunch of users' data and then try to use it with a new user, the performance declines 62%. Again, if the on-body location of the sensor changes, you see 66% decline in the performance. All right? So therefore, what we're doing is designing transfer learning algorithms, which basically this research is inspired by human beings' ability to learn how to learn, and so we try to design algorithms which allow us to transfer this knowledge from an old setting to a new setting without collecting data from scratch, and which is a very costly and oftentimes infeasible approach. Okay? So another challenge that we're facing is when you compare humans to machines, right? Humans learn in a continual manner, in the sense that, as new information becomes available, we learn, right? And this is a very critical component of human intelligence, that you can learn in a sequential manner as you're exposed to learning scenarios. But that's not the case with machines. Machines suffer from catastrophic forgetting, especially neural networks forget previous knowledge when they are actually exposed to continual learning tasks. And the main reason, again, is shift in distribution of the data. So in order to understand catastrophic forgetting a little better, let's look at the simple task. And we looked at this problem from general AI machine learning first, and then we saw implications of that in healthcare as well. So let's look at this simple task, handwritten digit recognition. Yeah? So with this, there are lots of kind of standard benchmarks for this and well-known architectures that you can use, and you can detect these digits with 99% accuracy, right? But in a continual learning setting, let's look at the sequence of tasks, where each task is a rotation of basically one of these, rotation of the images, right? So here is what happens. So with the first task, there's no rotation, so you can get 99% accuracy, right? Imagine the second task is rotating this to the left about 20 degrees, right? So you see a decline in the performance of the model with respect to task one. So the model starts forgetting task one. The performance declines to, let's say, 90%, while on task two, the performance is quite high. So let's do one more rotation. So you try to update the model using task three, and the performance on task one declines to 60%, and so on and so forth. So this is the problem of catastrophic forgetting with neural networks. So, and this is a relatively emerging area. So what we have been trying to do is to try to understand the catastrophic forgetting from a different perspective. We try to see how we can measure catastrophic forgetting. A lot of people have been trying to kind of modify the algorithm itself in a way that they can reduce the effect of catastrophic forgetting. So we're trying to see how we can quantify the amount of forgetting and what are techniques that can be used to actually deal with it. And so we have realized that by examining the loss curvature, we can basically tune our training parameters such as dropout, batch size, learning rate, and so on, in a way that we can minimize the effect of forgetting on neural networks. Another thing that we have done is basically we have tried to develop approaches that we can start with the initial solution and go to the optimal solution of multi-task scenario without getting trapped in a suboptimal solution. And the main reason for that is the continual multitask minima are connected by a simple, actually linear path. We're trying to understand how we can actually walk through that path to reach the optimal solution for this. So with these two kind of challenges of transfer learning and continual learning, I would like to conclude. I'll be happy to take any questions you may have.